Good evening to everyone. My name is Dr. Tirupati Venkateswar Reddy. Today I'm going to discuss my topic with the title of Thevenin's theorem. So, what is the statement of Thevenin's theorem? So, it states that any two-terminal linear bilateral network containing a number of voltage sources and number of resistors can be replaced by an single equivalent circuit consisting of a Thevenin voltage source in series with the Thevenin resistance. So if you observe this figure, so linear bilateral network, so it containing any two terminal linear bilateral network. So this is one terminal A, this is another terminal B. So it states that any two terminal linear bilateral network. So from the figure, if you observe that, so this is a linear bilateral network. So it having two terminals. So one is the A, so another one is the B terminal. So we are having one load resistance. So this linear bilateral network, so containing a number of voltage sources and number of resistors. So this is a linear bilateral network, whatever the dotted they represented. So in that linear bilateral network, so old number of voltage sources are there and number of resistors are there. So those number of voltage sources and those number of resistors can be replaced by an single equivalent circuit. So this is the single equivalent circuit. That single equivalent circuit, so consisting of a Thevenin voltage source, so that is VTH, in series with the Thevenin resistance, that is RTH, where VTH is the open circuit voltage between the terminals A and B. So this is also called as Thevenin voltage. So RTH is the equivalent resistance of the network. It is seen from the terminal A and B. It is also called as Thevenin resistance. So when you are calculating your Thevenin resistance, so you have to make it all the voltage sources are short circuited or replaced by internal resistances. So if you have any current sources, those current sources, you can make it as a open circuit test. So here RL is the load resistance. So this is the statement of Thevenin's theorem. So once again, I'm telling, so it states that any two terminal linear bilateral network. So this is a linear bilateral network. So it having two terminals, one is the A, another one is the B. That linear bilateral network containing a number of voltage sources. So here the number of voltage sources are there and number of resistors. So here the number of resistors are there. So those number of voltage sources and those number of resistors can be replaced by an single equivalent circuit. So this is the single equivalent circuit. That single equivalent circuit consisting of a Thevenin voltage source, that is VTH, in series with the Thevenin resistance. So next we will see what are the steps we are going to follow in order to determine Thevenin equivalent circuit. So let us consider a simple circuit and it is shown in below figure. So this is a simple circuit. So to find the current through the load resistance. So the following steps are to be followed. So the step one is, so to determine the current through the load resistance, how much current is flowing through this load resistance, we have to find means. So temporarily remove the load resistance from the terminals A and B. So we have to remove the load resistance from the terminal A and B. So that remove load resistance and it is shown in below figure. So this is the figure after removing the load resistance. So the step one is, so to remove the load resistance from the terminal A and B. So to calculate the current flowing through the load resistance. So the step two is the determination of Thevenin voltage. So, or else finding a open circuit voltage or Thevenin voltage between the terminals A and B. So when you are calculating your Thevenin voltage, so you have to keep it all the sources to their original positions. So you could not replace anything. So whatever the sources are available, those sources you can keep it as the original position. So and it is shown in figure. So this is the source they given. So we are keeping that source as well as the resistors they given. So those resistors also there. But here we are calculating the Thevenin voltage between the terminals A and B. So in above figure, if you observe that, so if you observe this figure, R1 and R3 are connected in series. So why? Because here you are having one closed loop and one open loop. So in closed loop, the R1 and R3 are connected in series. Then the total resistance are equal to R1 plus R3. According to the Ohm's law, I equal to V by R. So now you know R value. So that you can substitute here. So I equal to V by R1 plus R3. I equal to V by R1 plus R3. So now you know the current flowing through this circuit. So this I is flowing through the R1 as well as R3. Whatever the current is passing through the R1, the same current will pass through the R3. Now, the current through the R3 is I3, that is V by R1 plus R3. So, therefore, voltage across the resistor 3, that is V3 or V3H, V3 or VTH. So, is equal to I3 into R3. So, here we know that I3 equal to V by R1 plus R3. That I am going to substitute here. So now the voltage across the resistor 3 is, that is V3 over R VTH is equal to V by R1 plus R3 into your resistor value, that is R3. So this is about the Thevenin voltage. So whatever the drop is occurring through the R3, so that drop is the your Thevenin voltage. So the next step is to determine the Thevenin resistance. So, in order to find this Thevenin resistance or Thevenin equivalent resistance of the network, so we have to see from the terminals A and B. So that is shown in below figure. So when you are calculating this Thevenin equivalent resistance, so we have to make it, if any voltage sources are there, that can make it as a short circuit or replaced by the internal resistance, or else current sources are there, you can make it as a open circuit. So the circuit of Thevenin resistance is shown in below figure, but here we are calculating RTH is the from the terminals A and B. So that is there here in this figure. So in above figure, so in this figure, R1 and R3 are in parallel. In above figure, R1 and R3 are in parallel. So now the resistance is R1 into R3 divided by R1 plus R3. So now the circuit is, so once R1 and R3 parallel, that resistance is R1 into R3 by R1 plus R2. So now the circuit is, so R1 R3 by R1 plus R3 in series with your R2. So if you observe this figure, R2 and R1 R3 divided by R1 plus R3 are in series. So now the resistance, that means the Thevenin equivalent resistance RTH equal to R1 R3 divided by R1 plus R3 plus R2. So this is the Thevenin equivalent resistance. So we are seeing seen from the terminal A and B. So then coming to step 4. So in order to draw the Thevenin equivalent circuit, so what are the parameters we should know? It means one is the Thevenin voltage and another one is the Thevenin resistance. So now we know that Thevenin voltage as well as the Thevenin resistance. Once if you know the Thevenin voltage and Thevenin resistance, so we are going to draw the Thevenin equivalent circuit. So the Thevenin equivalent circuit is shown in below figure. So this is the Thevenin equivalent circuit. So that means So whatever the network is given, that linear bilateral network, we are replacing with the single equivalent circuit. So this is your single equivalent circuit. That is the Thevenin voltage in series with the Thevenin resistance. So coming to the step 5, here initially in the step 1, we remove the load resistance. So now what I'm doing here means, so whatever the load resistance I removed, that load resistance I am connecting back to here in original position where I removed from the terminal A and B. Now I am going to connect to that terminal A and B. So that is shown in below figure. So the Thevenin voltage is there, Thevenin resistance is there. So initially we removed from the terminal A and B. Now we are connecting the load resistance A and B in the same terminals. So in step 5, we are going to determine the current through the load resistance. So how much current is passing through its load resistance, that we are going to determine. So by applying the Ohm's law, so I equal to, so it is a closed loop. So here we know the Thevenin voltage as well as we know the resistance. According to the Ohm's law, I equal to V by R. So in the similar way here also, we want to find how much current is passing through the load resistance. That is IL equal to, so VTH by RTH plus RL. Why? Because RTH plus RL means RTH and RL are in series. So now we know how much current is passing through the load resistance. That is IL equal to VTH by RTH plus RL. So once if you know the load resistance, how much drop is occurring this load resistance, that we need to calculate. So in step 4, the potential difference across the load, that is the voltage drop across the load, VL equal to IL into RL. We know that VL, so that is we know that IL, so that is they given VTH by RTH plus RL. So now the total voltage drop across the load, that is VL equal to, so VTH by RTH plus RL. So this is the current flowing through the load resistance into RL. That means this is the total voltage drop of the through the load resistance. So this is about the Thevenin's theorem. So in the next coming video, we are going to see the problems of Thevenin's theorem.